So now we're going to go more specifically into the calculation of probability of failure on demand, right? So we have probability is equal to 1 minus exponential distribution exponential e to the minus lambda t divided 2 for average, right? So what does that mean? So what is a demand? Demand, it is when the equipment it is required to work, and when a demand happens, what is that time that demand could happen and I will be exposed not to be there, or the SafeGuard will be exposed not to be there and react. So what is that time? So it's the time at which a dangerous undetected failure may occur, and that time, and that is going to be in between two proof tests, right? And including the time to restore, and will not get detected by diagnostic coverage. Of course, it is a hidden failure, right? It is a dangerous undetected failure. So that's the probability of failure on demand that we're going to calculate. What is the probability? That probability has a time assigned to it, an exposure time to being vulnerable to a not responding. So we also have to understand what is an instantaneous value and what we understand by the average value. So here this graphic shows here that would be an instantaneous value, which just happened to be the value at which you have the average probability of failure on demand from that specific period of time. So you take that area, divide by 2, and then it will be a t divided by 2. So that will be the probability of failure on demand at that point. So that means that when you start up your system, your probability of failure on demand, it is much better. But as time goes by, when you get halfway between your proof test periods, then that means you're right there with the value that you calculated. Later on, then it keeps increasing, and that's what is called that is an average. So we see here, so the time, we already saw this curve before. So the probability of failure on demand will be equal to 1 minus e to the minus lambda t. That would be the instantaneous one, right? So we have to find out later on, we divide by 2 the time. That would be the average for that one, and then we can extrapolate that to having many periods of proof testing periods, and then we calculate the average there too. So for low demand mode, this would be the representation. So 1 minus e to the minus lambda t is a formula that represents what happens in nature, right? And that representation, we can work with that representation that will approximate very well how the equipment behaves and the probabilities of failure. So at the moment, I'm conveniently going to approximate these values when the lambda t's are very small. I can say that the PFD is very close to lambda t. So these two numbers will be very the same as long as those failure rates are very small. Right, so how small? Well, later on I'll show you what that means. But in order for simplicity to come up with the formula for probability of failure on demand, we'll do this. So we already saw this time diagram, and this diagram explains what would be our exposure time. So what is the channel equivalent mean downtime? Mean downtime, because it's between two proof tests, right? So one is t divided by 2. Also, not only is because it is between two proof tests. So I have here the time for or the failure rates detected. If they are detected by diagnostic coverage, then there's no problem. I don't consider myself to be exposed because I'm going to implement a contingency, or I might decide to stop the system. I might decide to trip the process, which is not a good idea, but that's an option. And if the risk is so high, well, that would be that case. I will not be exposed to that. But if I continue to run with implementing that contingency, then I will be exposed if then a demand comes. From the point of view, my sergeant when the function is not going to work. So that would be 1 minus the diagnostic coverage. That's what is left for being exposed there, including the mean time to restoration, right? The time that I discover what was wrong, and or either a stop, or either a proof test, or would discovered by a diagnostic coverage. So that time in yellow is what we call channel equivalent mean downtime. So that which lambda and which t, we already talked about the t, which lambda dangerous and lambda dangerous detected and undetected. So this one is the ones that we're most concerned with, the dangerous undetected. So we can divide our channel in two reliability block diagram boxes, one with respect to dangerous undetected failures and the ones with respect to dangerous detected failure. So probability of failure is equal to 1 minus e to the minus lambda t, or equals to lambda times t, and that t would be the time channel equivalent. So I have dangerous undetected, and the dangerous undetected, they are only discovered at proof test time average, so t divided by 2 plus the time that it takes to restore that system. And then also another part would be the addition of the lambda failure rates dangerous detected. So if I detect them, I still have the what is the time exposed there is the restoration time, right? So and they have a time equivalent. Channel equivalent would be the sum of the TC1 plus TC2. This is during proof test period, and this is during diagnostic coverage discovered when I'm restoring my system. So what do I do with this information? So the probability of failure on demand is going to be approximately to the dangerous failure rate times the equivalent channel equivalent time. So I already have lambda du times TC1 plus lambda dd times TC2, right? That would be already lambda times t, so lambda t, proof test time, diagnostic coverage. So I add the DC part. I know that lambda d equals well, lambda dd will be equal to lambda d times diagnostic coverage for the formulas that I presented before, and lambda du will be lambda d times 1 minus the DC part. So this is the diagnostic coverage part with respect to each section in there. And then I substitute the times by proof test time and mean time to restoration. So the t's now become t divided by 2 for average plus mean time to restoration. That's for the proof test side, and this will, the mean time to restoration will be for the diagnostic side. So from this point on, this will be the formula that we're going to use. This will be probability of failure on demand equals to probability of failure on demand average, because we took the average of there in that time, that as I showed you before. And this formula always goes towards low demand mode or demand mode or low demand mode. Look at what happens on high demand mode. On high demand mode, or we are not talking anymore about probability of failure rates. We're talking about frequencies. Okay, so it's totally different. This equation will not apply 100% when you have continuous mode of operation of a safety implemented function, right, or a controlled safety implemented function. And we'll talk more about that later on. So what we went through is exactly what happens, or the way that IEC 61508 Part 6 Appendix B22 page 5153. There you will find exactly the same not explanation. The explanation I gave you, I hope is simpler than what is written in IEC. It brings you more in there, and this will be the formula that you will find exactly in that page. So IEC 61 SafeGuard profiler complies with the formula inside or that explains IEC 61511 and 508 -6. So what is SIL verification? Again, all these factors that affect there. So now let's talk about the what we're talking about, the test coverage factors, or imperfect proofs testing. The standards, they don't go too much into this equations, or they don't consider this. They assume that you're doing your work. They assume that you're really testing your equipment. They assume that the equipment that you chose, it is fit for purpose and for the intended purpose that you need that equipment. Those are assumptions that are perfectly okay, and that's why we assume that our equipment has a constant failure rate, as long as we say that we're doing what we said that we were going to do, which is to follow the IEC 61511 best practices, right? So the question that I showed you before does not take into consideration detection of the dangerous failures detected by proof test. Okay, so if the proof testing is not 100% effective, so we said that we leave something inside there, so some never detected dangerous failures that might still lingering in there forever. So the residual dangerous failures might not be detected and remain undetected for the life of the system. So which might be the time the system is replaced with a new one at the end. Of course you have to do that, or decommission, or you don't use it anymore. So the missing probability of failure on demand that was not there can be calculated for situations in which the proof test is not considered to be 100% effective. Those would be rare occasions, I hope. So test coverage is the percentage of how effective is this test coverage. In the same way that we went through the diagnostic coverage, well, we used a similar approach for test coverage with respect to the lifetime of that equipment. So we have our probability of failure on demand normally that we calculated before, and we have to add, remember that I said that you have to add this every time that you do a proof test, you have to add a little bit that was left over in there. Well, that's the part that we have to add until the end. This case we add all of it, the safety life cycle, or the lifetime of that device. So that's what's happening also in the software, right? Safety failure fraction. So the safety failure fraction is the fraction of the overall random hardware failure rate, a device that results in either a safe failure or a detected dangerous failure, right? So we talked about already that. So there are safe failures, detected or undetected. They're nonetheless safe or spurious, and then we add the detected dangerous ones that we through diagnostic coverage. So diagnostic coverage has an influence on the safe failure fraction. What is important to know about this safe failure fraction is the dangerous failure fraction, and we will see some tables that are up here on IEC 61511. Those tables tell us that if we have a piece of equipment that has more than 40% dangerous failure fraction, then that equipment is not good enough, and that we need two of them, or that we need some type of redundancy in order to account for integrity of that system, or not integrity, but the safety integrity level has to, or the SIL level, in order to be able to reach that. One piece of equipment by itself will not be enough if it has more than 40% dangerous failure fractions, or more than 60% safety failure fractions, or less than 60% safe failure fractions. So safety failure fractions might alternatively be defined as the conditional probability that a failure is either a safe failure or a detected failure. Okay, so, and here are these tables, and they come from IEC 61508. And for example, and this would be for hardware fault tolerant table with respect to type A equipment, or we have type B equipment, and they are explaining there. So type A equipment, it is for non-intelligent or equipment that doesn't have, for example, too much diagnostic coverage, or sophisticated. Type B equipment will be, for example, your logic solver. All right. So let's talk about, for example, about the type A equipment. So what is the safety failure fraction if it is less, if it is greater than 60%, as I mentioned before? Then and if it is greater than 60% and I need a SIL 2, then I have to have some sort of redundancy. So my hardware fault tolerance is 1. So that's the way that I read these tables. So what does that 1, 0, 1, 2 means? Means that a hardware fault tolerant N means that N plus 1 faults could cause a loss of safety function. So this N plus 1 faults, so there's a difference between a failure and a fault. A fault doesn't mean the loss of the functionality of the function, that your safety interventive function is going to work, right? So it's just a fault inside there, but can still perform the action, can still perform the function. So if I have 2 of them, so that means that 2 faults will have the probability of causing the loss of the safety function, right? So that's what it means, that hardware fault tolerant. Then we go to common cause failure.